Hi, I'm Dr. Jacob Hudis, and welcome to this video titled Macroscopic Quantum Energy Leap. Join me as I demonstrate a captivating experiment with a thin, elastic steel plate that functions as a spring. By gradually adding energy to the system, the steel bends and stores potential energy until at a critical point, it suddenly leaps into a new energy state. This striking behavior is a perfect analogy for how electrons transition between energy levels in quantum mechanics. Quantum mechanics describes electrons as waves that are spread out over an atom.
Oh my!
Each specific wave pattern corresponds to a distinct energy state of the electron. This cartoon shows allowed wave patterns that satisfy the proper boundary conditions. This wave pattern would not be allowed because there's not an integer number of wavelengths as you go around the atom at that radius.
To visualize this, imagine standing waves on a stretched membrane, like the surface of a drum. These wave patterns are shaped by boundary conditions, physical constraints that define how the wave can form. In an atom, the structure of the atom itself imposes these constraints, and the resulting standing wave patterns correspond to the electron's possible energy states.
Each standing wave represents a distinct energy level. When an electron absorbs or releases energy, it can make a sudden, discrete transition, or quantum leap, between these states.
When studying quantum mechanics, it's helpful to begin with one-dimensional problems. Simplifying to one dimension removes unnecessary complexities, allowing us to focus on the core principles of quantum physics. One-dimensional quantum systems aren't purely theoretical, they can be created and studied in laboratories. A classical example is a particle in a one-dimensional box. In this system, the solutions are electron wave functions that form standing waves along a single line. The energies are quantized, meaning they can take on only specific values determined by an integer quantum number n.
Fantastic.
If you've taken quantum mechanics and solved the particle in a one-dimensional box, you know that these are the wave functions for the electrons. They go on to infinity, and there are these discrete wave functions, and each of them corresponds to one energy, one allowed energy level for the system, where n is the principal quantum number. These wave patterns also evolve over time, just as water waves or any other waves change and move. An electron can exist in a single standing wave pattern or in a linear combination of multiple patterns, embodying the richness of quantum behavior. And now let's move on to the experiment.
This invention features spring steel plates that are mechanically compressed, increasing the system's energy. At specific loads, abrupt crest transitions occur, providing a powerful analogy for visualizing concepts in quantum mechanics.
This experiment provides a unique opportunity to observe with the naked eye a macroscopic analogy to a quantum leap, a phenomenon where an electron in an atom jumps from one energy state to another. It offers an excellent way to visualize one of the fundamental concepts of quantum mechanics. What we see here is a wave pattern. Unlike quantum mechanical waves and standing waves, which evolve over time, this wave pattern remains stationary. However, there's a striking parallel to quantum mechanics. When enough energy is introduced, the system undergoes a sudden and abrupt transition to a new energy state.
As for whether the behavior of the spring steel has a direct quantum mechanical explanation, that's less clear. Regardless, this experiment remains a fascinating demonstration and a powerful tool for illustrating the idea of quantum transitions. What do you think? Does this phenomenon have underpinnings in quantum mechanics, or is it more of a classical effect? Leave your thoughts in the comments section below. Regardless, we can all agree it's a really cool experiment.
If you want more information on this experiment, please look up the paper Quantum Spring Investigation, Engineering Analysis, Test Evaluation. You can contact Lee Guthrie of Brownsville, Tennessee for more information on the experiment. AcePhysics.org.
Oh boy,
Math and Physics Tutoring with Dr. Hudis.